Hello again. This is Math 2232 coming to you from the College of DuPage. The title of this lecture is Power Series and Functions. As always, please be an attentive listener while watching this video. With this lecture, we start talking about how to represent functions with power series. Let's start off with one we already know how to do. Although when we first ran across this series, we didn't think of it as a power series, nor did we acknowledge that it represents a function. So recall that the geometric series is the summation n equals 0 to infinity a times r to the nth power, and that is equal to a over 1 minus r, provided that the absolute value of r is less than 1. Also, don't forget that if the absolute value of r is greater than or equal to 1, the series diverges. Now let's consider this series, but take a to be 1 and r to be x. Then what happens is this equation line becomes the summation n equals 0 to infinity x to the n equal 1 over 1 minus x, provided that the absolute value of x is less than 1. Now if we turn this around a bit, starting with this side, we can say that f of x equal 1 over 1 minus x can be represented by the power series, the summation n equal 0 to infinity x to the n, provided the absolute value of x is less than 1. Now this provision here, provided absolute value of x less than 1, is important. You see, we can clearly plug any number other than x equal 1 into this function, but we will only get a convergent power series if the absolute value of x is less than 1. That means that this power series represents that function only when the absolute value of x is less than 1. So the inequality talked about up here will only hold if the absolute value of x is less than 1. Any other value won't work. Note as well that we can use this to acknowledge that the radius of convergence of this power series is r equal 1, and the interval of this convergence is absolute value of x less than 1, or x is between minus 1 and 1. This idea of convergence is important here. We will be representing many functions as power series, and it will be important to recognize that the representations will often be valid only for a specific range of x's, and there may be values of x that we can plug into a function that we can't plug into the power series. In this lecture, we're going to concentrate on representing functions with power series where the functions can be related back to equation 2. And equation 2 is the one we were just talking about. F of x is equal to 1 over 1 minus x, and that can be represented as summation n equal 0 to infinity of x to the n, provided the absolute value of x is less than 1. In this way, we'll become familiar with some kinds of manipulations that we sometimes need to do when working with power series. So, the first example, find a power series representing the following function: g of x equal 1 over 1 plus x cubed, and determine its interval of convergence. You know what to do. Let's see how you did. All right, so what we're going to do is we're going to take the given function and we're going to rewrite it as g of x is equal to 1 over 1 minus, and this is minus x cubed. And if you think about a minus times a minus being a plus, you'll see that this is another representation. But now we have this in the form of 1 over 1 minus something. And so the minus g cubed and g of x hold the same place as the x in our earlier equation. Therefore, all we need to do is replace the x with minus x cubed, and we have a power series representation for g of x. So we have g of x, the one we started up here is this, but that's the same thing as the summation n equals 0 to infinity of, and this is minus x cubed whole to the n, provided minus x cubed, the absolute value is less than 1. You see we're plugging into the same function. So now all we need to do is a little simplification. We get g of x is equal to the integral from, not the integral, the summation rather, from n equals 0 to infinity of, this is minus 1 whole to the n, this is x to the 3n, provided that the absolute value of x cubed is less than 1, and that's the same thing as the absolute value of x being less than 1. So in this case, the interval convergence is the same as the original power series. Now this won't always happen. More often the new interval convergence is different than the original interval of convergence. So notice now that we have g of x, which is this, is represented by this power series for this radius of convergence. Another problem, find a power series representation for the following function in a determinate interval of convergence. And again, these are excellent practice problems both for now and looking forward to reviewing for the final. So h of x in this case is 2x squared over 1 plus x cubed. Now this function is similar to the previous function. The difference is that the is in the numerator. And at first glance, that looks to be an important difference. And since the equation for the geometric series didn't have an x in the numerator, it appears that we maybe can't relate that to back to that. But we'll learn differently with this example. So what we're going to do is we're going to write h of x as to being 2x times 1 over 1 plus x cubed. But we know that 1 over 1 plus x cubed can be written this way. So we have a 2x squared on the outside, provided the absolute value of x is less than 1. That's the interval of convergence for this. But we now can distribute this 2x squared across this sum, just as we did the distributive property for finite sums. So when we multiply all the way through by 2x squared, the exponent becomes x to the 3n plus 2. The 2 goes in, and you still have the minus 1 to the n. So h of x is equal to this, provided, and again, it is when the absolute value of x is less than 1. Let's find a power series representation for the following function in a determinate interval of convergence. This is f of x is equal to x over 5 minus x. And again, these are good problems to practice. So again, what we're going to do is write this as f of x is equal to x times 1 over 5 minus x. But this 1 over 5 minus x isn't exactly what we want. So we're going to have to work on that a little bit. And let's just start talking about, so what do we need to do with this? G of x equal 1 over 5 minus x. And then we can just distribute the x and we'll be done. Well, what we notice is that if we factor a 5 out of the denominator, we have then 1 over 5. And here now we have 1 minus x over 5. Well, now all we need to do is get a power series representation to replace x in 3 with x over 5. And this 3 is this, equation that we have over here. So doing this, we're going to put x over 5 in for x, and we'll raise that to the nth power, and we have the 1/5 constant out in front. And this is provided that the absolute value of what we have here, it was the absolute value of x over here, but now it's the absolute value of x over 5 is less than 1. That means the interval of convergence is going to be the absolute value of x less than 5. So that is what g of x is. And now we can go back to f of x. F of x is x times that. That's x times this is what we got for this power series. And notice that if I take the 5 inside, I get 5 to the n plus 1. So this is going to be equal to the that's an equal sign. The summation n equals 0 to infinity. This is x to the n plus 1 over 5 to the n plus 1, and the interval of convergence is the absolute value of x is less than 5. So now we have an idea on how to work to find power series representations for some functions, and these were all related to the geometric formula, but we can use any formulas that we have, and we're going to be doing more of this in the future. We now need to look at some further manipulation of power series that we will do on occasion. So we need to discuss the differentiation and integration of power series. So let's just assume that we can differentiate the power series term by term. And so let's start with f of x equal this power series, and that is c0 plus c1 x minus a, c2 x minus a whole squared, c3 x minus a whole cubed, plus dot dot dot. Thank goodness for dot dot dot. So if we differentiate term by term, we'll get f prime of x is equal to the derivative of this, and let's just see if we do it term by term what happens. So we get c1 plus 2c2 x minus a plus 3c3 x minus a whole squared plus dot dot dot, and this is going to be the summation n equal 1 to infinity of n times cn times x minus a whole to the n minus 1. So I took the exponent times this, and I reduced the power by 1, and the constant's along for a ride, and I do that for every term in the series. Now, if I take formulas for higher order derivatives, I'll just be taking the derivative of this. This was f prime, so this will become f double prime, and this will be the summation n equal 2. Notice that some of the earlier terms become constants, and I take the derivative. So it's going to be n times n minus 1 times cn x minus a whole to the, this is n minus 2. f3 is going to be the summation n equal 3 to infinity n times n minus 1 times n minus 2 cn, and this is parentheses x minus a whole to the n minus 3. Note that even though this sum starts at n equal 3, I could start at n equals 0 because this would be 0 there, n equal 1 would be 0 here, and n equal 2 would be 0 here. That's a technique we often use in differential equations. So notice the initial value changes to acknowledge that term from the original series goes to 0, but those are going to be 0 terms because of the derivative anyway, as I just mentioned. Okay, let's talk a little bit about integration. Now let's pretend that we can integrate a power series. So we have f of x equal this power series, but now we're going to integrate it term by term. So the integral of the sum is the sum of the integrals. We're assuming that this is true. And then you can pull this constant through the integral and integrate this. And the integral of this is going to be x minus a whole to the n plus 1 all over n plus 1 plus a c. And this c is all of those little c's added together. That's the capital C. And that's outside the series here. So let's summarize some of our ideas and notions before moving on. You see, you can, this is, I say it's a fact, it's really a theorem. So if f of x is represented by this power series and has a radius of convergent r greater than 0, then f prime and the integral of f of x dx can be done term by term, and both of these also have a radius of convergence of r. This is a powerful theorem. Now this is a theorem, and we're not going to prove this, but you should make note that it really is a theorem, and it's not obvious that you'd be able to do that. This is one way that a power series is much like a polynomial. So we're using this result, and you should use this result as well. Moreover, sometimes when you take the derivatives, you will lose an endpoint, or perhaps both endpoints of the interval of convergence. Similarly, if you integrate, you make this function smoother, you may gain an endpoint. But neither of these additional facts result in changing the radius of convergence. So let's look at how we can apply these facts to get some more power series representations of a function. So suppose you have g of x is equal to 1 over 1 minus x whole squared. And again, these are good problems for you to know how to do. So to do this, let's notice that 1 over 1 minus x whole squared really is the derivative of 1 over 1 minus x. You see, this is 1 over u du, but when I do du, I get another negative sign. So this is going to be u to the minus 2 du dx, and that's why the sign works out. So this is true that if you differentiate this, you will get this. But we have a power series for 1 over 1 minus x. So what we're going to do is we're going to take the term by term derivative of that power series to get a power series representation for g of x equal 1 over 1 minus x squared. Okay, so this one then is equal to the derivative of that, which is the derivative of this term by term. This is going to be the summation n equal 1 to infinity of n times x to the n minus 1. And since the original power series had a radius of convergence of r equal 1, the derivative will have a radius of convergence of r equal 1 by the theorem that we quoted. And so another formula for you to remember about a power series expansion. Let's move on to another example. Find a power series representation for the following function. H of x equal the natural logarithm of 5 minus x, and determine its radius of convergence. Again, these are excellent practice problems both for now and for the future as you prepare for the final exam. Well, note that if we integrate this expression, 1 over 5 minus x dx, a simple change of variable tells us that this is minus the natural logarithm of 5 minus x. Make sure you follow this calculation and know where the negative sign comes from. But earlier, we found the power series representation for 1 over 5 minus x in an earlier example. And what we found out that, well, we had a power series representation for this. So if we integrate the power series representation term by term, and here we're acknowledging the minus sign and we're moving the minus sign to the other side, we get this. We integrate this term by term after we use the representation that we have. This is the representation that we had for 1 over 5 minus x. That was an earlier example. So now what we're going to do is we're going to integrate this term by term. We add 1 to the exponent and divide by the new exponent. So you see, we find out that this function is represented by a constant minus the summation n equals 0 to infinity x to the n plus 1 all over n plus 1, and this is 5 to the n plus 1. Now we have to find the constant of integration, or we can find the constant of integration by plugging in any value of x, and let's plug in x equal to 0. And so if we plug in x equal to 0, all of this is 0, and so c is equal to the natural logarithm of 5. And that's what we did here. And so the final answer is the natural logarithm of 5 minus x is ln of 5 minus the summation n equals 0 to infinity x to the n plus 1 all over n plus 1, and also divided by 5 to the n plus 1. And the radius of convergence is still 5. So we really can do a lot with these representations, and we're going to be doing more of this as we go forward. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We all are in this together. God bless you all.